Welcome back everyone. So, we were talking about manifold. So, manifold is a topological space in which we can locally coordinatize it, right. So, it is made of three things. One is atlas. So, atlas means all the points of the manifold is now put it into RD in small patches, right. Let us take some example and counter example. So, of course, RD is a trivial manifold, it is a manifold. We learn what is trivial and non-trivial, but it is definitely, because RD you can always map every point to RD, and that is my definition of manifold, and it is also topological space. Okay. And it is trivial because it does not have any curvature, so you can actually define the same map at all points. Whereas for non-trivial topology and manifold, we will not be able to get define the same x, same homeomorphic to RD at every points, and this is where things becomes interesting. Okay. And S1 is also manifold, because S1 is this, and you can take every point and define a neighborhood, and one can map it to a flat region which is RD, which is R1. So, it is a manifold, it is a one dimensional manifold, and this is also manifold because I can take every so it is a cylinder, you can take every point and you can map it to R2, we need two coordinates, right. So, and can be theta and z and so on. Now, let us take a counter example, a knot in which, so knot is not topologically same to S1, we talked about it earlier, and it is also, it is topological space, but it is not a manifold, because at this point we cannot uniquely define a coordinate system. Somebody says that I will define a coordinate system by looking into this neighborhood, in which I will define a left handed coordinate system, and another person can say I will define a right handed coordinate system like this. So, and they do not agree with each other. So, that means at this point you cannot define a unique coordinate system. So, it is not a manifold. And D brane, which is used in string theory, is also like you have some plane and you have a point coming out. So, at this point you cannot define a coordinate system. So, it is also not a manifold, but they are topological space. But for us, we will mainly be we will only be talking about manifold in this course. So, let me take two more examples. Again, I will not go into details, you will see that with many examples later. Let us talk about some Hamiltonian, which is written in terms, it is a 2 by 2 Hamiltonian, and you can always write in terms of Pauli matrices with some identity, which is the diagonal term. And then you will have some sort of a, for if I take any energy eigenvalue and draw it in this coordinate system d1, d2, d3, which can be parameterized with some tight binding hopping and things like that, and that will sort of draw some closed or open set, and that is a manifold. But one point I wanted to make is that here the Hamiltonian is parameterized with 4 of them, but not all 4 of them are required to define a manifold. This is actually just a constant term, just a constant shift of the energies. It does not enter into your energy eigenstates. So, it does not really this one does not contribute much to your energy eigenspace and any topological phase. We will see those later. But here the 3 of them contributes to make a manifold. So, it is actually, even though you had 4 variables, but it is actually a 3 dimensional manifold. Okay. And another one, I do not know how many of you have studied free energy field theory, Ginzburg-Landau theory. If you have studied, you can identify. If you have not studied, when you will study in statistical mechanics, you will see that. And then also when you do renormalization group theory, so free energy can be written in terms of fields or order parameters with some parameters. So here u, v and other things can be parameters. And then you can say that this free energy in u, v and other parameters make some, this is my f, some constant value of f. Does it make a manifold? It turns out that not all parameters make a manifold, and something called irrelevant parameters in the renormalization group theory, that makes a manifold, but not all of them. So, that means not all parameters are required essentially to define f, but only some of them, and that will define you the dimensions of the manifold. Okay. And Fermi surface is of course a manifold, and we talked about that. It is a topological space and also a manifold. All right. So, now we learn manifold, and manifold in addition to a topological space has one more thing called atlas. Now, let us talk about the map from one manifold to another manifold. For every such set with structure, you need to have a map which has to keep the structure same. So, here for manifold also we need to have a map. So, here we are talking about two things, and we have to really be careful about what they are. So, we are talking about two things. One, within the same manifold between different charts we have a transition map, right? And if this transition map are k times differentiable, then that is called a C4 compatible map, or generally one would call C4 manifold, CK, k times differentiable. So, CK compatible topology, a manifold. And in most cases we are interested in the infinite infinitely differentiable. So, when k goes to infinity, where we can define Taylor expansion, for example, these are called C infinity or smooth. Smooth is continuous and differentiable manifold. So, you do have a continuous map which is true for any topological space, but now also that map is differentiable infinite times. So, that is called smooth manifold. Okay. Now, the second one is a map between one manifold to another manifold, in which set, topology and atlas, all three should be able to map. So, every open sets should be mapped to every open sets, and they are also differentiable, and that is called a differentiable map. If it is k time differentiable, it is k times. If it is infinite times, then it is k infinity differentiable map. Okay. So, it is a map between m to n manifolds. And if this map is bijective, you can go from this direction and that direction, so it is one to one, that is called diffeomorphism or diffeomorphic map. So, it is homeomorphic, that was for topology, but now a homeomorphic map that is differentiable, it is called diffeomorphism. Okay. And it's and such topology is called diffeomorphic manifold, or not topology, manifold. Okay. So, if phi is a smooth bijective, that means inverse also is differentiable, then phi is called diffeomorphism, and we define it this way. So, roughly speaking, again these two manifolds are same under a homeomorphic which is differentiable. The example will be of course these two, which is just distorted, but at every corner you have a smooth, so you can actually define so it is a one to one, and also all points are differentiable. But if I have a smoothly deformed to a rectangle, you see that at this edge you cannot define a differentiations because there is a discontinuity in the curve. So, they are homeomorphic, because it is continuously deformable, but not diffeomorphic. Alright, so that gave you a quick introductions to manifold and diffeomorphism between different manifolds. And now, and we define also functions, but now we have to define the remaining things called vectors, tensors, and some particular form of tensor called form, and also tensor at tangent space. So, this is important in many way. One, obviously to define differentiations and to define calculus, but also roughly speaking vectors and tensor, they are all defined in a coordinate system with a unit vector. So far when I said that in manifold can be mapped to RD, and I roughly said that you can, so that means you can define a coordinate system. I mean, it was loosely speaking. To define a coordinate system you need unit vectors and all, and that is done through tangent space, not with tuples. Tuples are just a functions and a d number of functions, but now we are talking about vectors and unit vectors. For that we need the tangent vectors. So, how it is defined? So, derivatives and calculus are mainly defined, you can define at a point, but eventually we are interested on a curve, right. So, the derivative on a curve is roughly called directional derivative. So, let us take the analogy from the classical mechanics that we have learned how to define a directional derivative. So, let us say I have some curve, and here the curve is defined in RD. So, it is a curved in kind of a coordinates of some particle moving in 3-dimensional space, and as a function of time that gives you the how the degrees of freedom is moving in time, that give you the curve in space, or you can even go and do it for phase space. And then we have some functions defined on that curve, on this coordinate which are changing in time because the particle is moving, and there can be some explicit time dependence also. So, if I have such a functions on that curve, how do you define the functional derivative? So, it is nothing but how f changes along the path as the particles are moving, how its density is changing. And what we do is that we define a total derivative in time, and that is my directional derivative. We will see that. And that is how all the equations of motions are also defined. So, how do we define? We use the chain rule. We first take the derivative of f with respect to x or r, if you like, the components, and then how the x or r are changing in time, that gives you the velocities, and then you have a dot product because each component wise it is done, and then you have this explicit time dependence. So, it has a partial change of f in time. And for the time being, let us assume that there is no explicit time dependence, okay, just for simplicity. Let us ignore this term. So, then this term you can actually define as a operator form. How do you define it? So, the total derivative is these vectors for each coordinates and then a partial derivative in space. So, if you act on f, that will give you the directional derivative of f along that path, and the path is defined by the v. So, v, so if I have this r, at every point I am taking a directional derivative. So, v is nothing but a tangent vector at this point p on this curve. So, then it is actually the v which gives you the directional derivative operator. and what we can do is that we can define a vector v with v mu are the component, and we can call this guy as unit vector, and this is the component. So, v is kind of a vector, tangent vector, and these are the components of the tangent vector, and this one we can call it as unit vector or frame vector. Okay. So, it is actually v acting on f gives us directional derivative. Okay. So, we can use this analogy and build how the directional derivatives are defined on an abstract manifold. Okay. And this is the definition. A directional derivative v along a curve, and this is how the curves are defined on a manifold. It is from some interval that gives you a curve. So, directional derivative v along a curve at a point P on the manifold M is a tangent vector to the curve at P. Okay. So, v is a linear map acting on some function that takes you from the manifold to a real number. And you can read this. So, I have some function and I want to take a functional derivative, a directional derivative on this curve. So, this is how. So, you first draw the curve, and after you go to the map and you take a derivative. It is just a notation. Okay. It is a complicated notation, we will not use much, but let me just introduce you. And what you get is the functions on this curve and this derivative. Okay. So, it is nothing but acting this tangent vector on this curve, acting on this function, and that is the directional derivative, which is nothing but a number. Okay. So, that is the definition of directional derivative of a function along a curve on a manifold, which is nothing but acting the tangent vector. So, now it becomes interesting. So, what happened is that I am interested a local derivative, right, and there can be many curves, and many curves may be homeomorphic or homotopy to each other, and some of them may not be. So, in principle you can have many curves, and then how do you sort of organize them? So, obviously if I think of having many curves, I will have many vectors, but then you can say that how many such vectors are linearly independent from each other, right. So, that means all the vectors that you can define at a given point along all possible curves form a space, and it is a homework, you can figure out that they actually form a vector space. So, they actually follow the axioms of vector space. So, there is a closure property under addition, and there is a closure property under a scalar multiplication, and so on and so forth. And that is called tangent space. So, tangent space is a vector space of the tangent vectors. And how many such tangent vectors should be there, linearly independent vector? That depends on the dimensions of the manifold. So, if it is a d dimensional manifold, there will be d tangent vectors. So, if I have a space, I can also define a unit vectors. So, any vector, then we can expand in those unit vectors. Okay. So, there will be d number of unit vectors for this vector space, and sort of defined like this. And C infinity are called curve. So, I am not going to use much functions, infinitely differentiable functions, all functions that form a space on this manifold are sometimes denoted by this. Okay. So, for all curve that you can draw, which are infinite times differentiable, there will be vectors. So, you take all these vectors, form a set, and you can see that, you can show that that forms the vector space. This is how that is denoted. So, this is the tangent vector that we denote. So, it is like a T at point P on this manifold. That is the definition. It is a tangent space. Alright, as I alluded, now we have to define the components and basis, and we sort of roughly talked about these two earlier. Okay. So, I define a vector with components and unit vector, and because now we are talking about more specifically the tangent vectors, they are nothing but the directional derivative, and these are the velocities, and these are the partial derivative in x. So, generally the components are defined in RD, in locally by mapping from every points on the manifold to RD. So, they are defined on a chart. Okay. So, that is what I am doing it. So, there are mu corresponds to x1, x2, x3, d number of d is the dimensions of the manifold. So, there are d tuples, and these are the tangent vector component of the tangent vector, and these are the partial derivative for each tuples. So, these are the contravariant because I am sort of using the index in the upper one, these are the contravariant, and these are real component, and we will call this as unit vector or basis vector or frame vectors of this vector space, okay, which are nothing but the partial derivative. Okay. So, then the directional derivative on a function is as we defined earlier, and it is defined on a chart. So, it is the tangent vector and the partial derivative of the functions along those directions. But when we define a vector and vector space, we also have to define the length, because length is something that has to be invariant under the rotations and coordinate transformations and so on and so forth, and length is also something that we measure. So, how do we define length? For a general vector we take a derivative, but in more generally it is like an inner product. To define an inner product we need to have a dual space. So, now for every tangent vector to define the length we need to have a dual space of those tangent vector, which is called cotangent vectors, cotangent space. Okay. With that we should be able to define the inner product. So, for every tangent vector, to start with a tangent vector, for every vector there must be a dual space towards a tangent vector, such that if you multiply those two and sum over all such component, you should get the inner product. So, dual space is defined modulo how the inner product or length should be defined. That is what it means, and that is how the definition also goes. For every tangent vector, tangent space, the dual tangent space, cotangent space denoted by star, such that it consists of V star, which are the dual vectors, such that it acts on every elements of your tangent space and give you a number, and here number being the length or the inner product. So, V star V, and sum over all the components, it should give you the length, that is the R. So, this is how the definition is explained. So, acts on a tangent vector and produce a number or linear R, which is the length of the vector through inner product. And elements of the tangent vector, so the R V star are called the cotangent vector, or generally we denote by omega. For every V, the V star or omega, omega will save it for a more for a particular type of cotangent vector, but for the time being let us use V star or omega as maybe both, without distinguishing them. So, now how do we expand it? So, for vectors we expanded it in the partial derivative, and partial derivatives being the unit vector, and then we had the components. The cotangent vector is defined with this total derivative or the elements, the line elements along each tuples. and these are the components. So, omega, which is df, and or rather let me add this also. So, that is like v star along the same curve at some point acting on f is denoted as omega or df. One would sometimes define it as df. Okay. And then these are the components which we will call omega, or if you like the component on the charts, and then these are your unit vectors. And then obviously the unit vector must be must have the orthonormalizations, and this is how it is defined. So, this is roughly defined like x mu x nu, which is equal to delta mu nu as it is written. So, they are orthonormalized. Okay. This is slightly tricky on how to do this mathematics and all. So, as you can see that the inner product is defined with this unit vector acting on here. That is how the inner product is defined. Okay. Since we will not use much of these things, so I will not get into the details, but those who will be interested, you can go through it. The inner product, and you can generalize to inner product between a vector and its and another covector, which will be like I expanded in the basis, the cotangent basis, and here I expanded in the tangent basis, and then I take mu and nu. So, I take this component and that component and the inner product between this and this, and this inner product is defined like this. And that by definition is delta. So, we will have this. So, it's each components are multiplied and then you sum over all them, and that is the inner product. Okay. And that is a number. All right. So, okay, one more quick thing. So, there is some more mathematical thing one defines, and if you read any advanced papers on topology in condensed matter, they use the terms called push forward and pull back. For the rest of my this course, we do not need it, but let me just introduce in words. So, the map from tangent space to tangent space between two different manifold is called push forward, and the map, which is generally inverse map between cotangent space to cotangent space, is called pull back. Why we take the inverse map? Because a cotangent space is defined first after defining the tangent space, right? So, because they are tied by the inner product. A cotangent space is defined from a tangent space such that you get an inner product to be 1. So, that is why first you define the, first you map it to the tangent space, then you define the cotangent space, then you go back. So, that is why it is called pull back. But right now it is just a map of the differentiations. So, if you take a simpler example, it is like going from here we define x partial derivative, which are the frame, and here let us say we define y and nu. So, it is like, or maybe some theta. Here maybe we used a tangent space in the spherical coordinate, here we define in the Cartesian coordinate. That is a map from this partial derivative to that partial derivative is push forward. Okay. And here it will be dy mu to dx mu will be pull back. All right. So, this gives us a detailed understanding of vectors and inner product and cotangent space, and I will stop it with the definition of tensor. Okay. So, tensor is a more general version of what I have talked about vectors. So, what we did for vector is, we will come back to this n and m later. So, we took a vector and so we took a vector and define in the component wise mu, and we define the co-vector as by covariant vector, right. So, now you can actually combine these two and generalize it to higher dimensions, and that is what tensor is. So, M and N, so it is a N and M type tensor in which there are M covariant, so it is defined in the the covariant derivative or in the basis of covariant derivative, and N cotangent variables. Okay, that is how it will be defined, and these are the components. So, a 0-2 tensor is generally called T or T2. So, that is like covariant tensor, 2-dimensional covariant tensors, like our conductivity tensor is a 2-dimensional tensor, and you can have a covariant sorry, this is contravariant tensor, and you can also have a equally covariant tensor in which it will be defined in the cotangent space. So, it will be mu1 mu2 this way. The form is a special type of tensor in which you do not take any combinations of mu1 mu2. Mu1 mu2 runs from 1 to d when a d dimension is 1, but you take a surface integral sort of a surface term, if you like, dx dy, or rather you take a antisymmetric product between them, which is called wedge product. And if you define a tensor in that basis, and here we are defining a 2 form, you can generalize to n form like that, and this is called wedge product. So, wedge product is it is antisymmetric between the two indices. So, that means they have to be different. So, it is like x and y or x and z, but not xx. Xx will be dx square, that is like a line element. So, this is more of a defined in the area basis, if you like, rather than line basis. So, when x equal to mu equal to nu, it is 0. So, this actually if you define a tensor, this is antisymmetric with components in the off diagonal term and here the negative, but the diagonal terms are 0. Okay. So, one example is of course your Levi-Civita beta. Okay. And the tensors that we define in this wedge product or 2 form basis are the tensors that we will encounter in this course all the time, being electromagnetic field being a antisymmetric tensor, right. This is a partial derivative of the vector potentials, and this is antisymmetric. Okay. So, this is a 2 form. It is a cotangent or cotangent tensor or cotensor if you like, but it is a special tensor compared to this. It is defined with a wedge product. The vector potential is called 1 form, and field tensor is called 2 form, and one can generalize to higher form. We do not need it in this course, and the Berry connections we will have is also 1 form, and the Berry curvature will be 2 form. Okay. So, with that I will stop now, and we will start more about the calculus in the next class.